Good afternoon. Good afternoon, everyone. Welcome to the Foreign Correspondents Club of Japan. It's a huge honour for the club and a very great personal pleasure for me to welcome Professor Morita today to talk about something truly extraordinary, the discovery of a new the creation of a new element, which, of course, you've seen the press. It's the first time that a team of Asian physicists have naming rights for an element, and it's a wonderful thing for Japan. It's a wonderful thing for RIKEN, and it's a particularly wonderful thing for Professor Morita. I want, if you can, to try and imagine bombarding bismuth with zinc. And then for just a tiny fraction of a second, creating something that wasn't there before, but is fundamental to our universe. I think most of the people in the room can't imagine that, but our guest today was able to, and was able over many years to pursue relentlessly the achievement that he and his team were able to make last year. And we welcome a professor who will give us a presentation on exactly that process and the many twists and turns that it took. So, Professor, thank you so much.
Welcome. Thank you very much for kind introduction. And first of all, I'd like to thank all of you that's inviting me this place. And the last day of year 2015, and early in the morning, I have received one email telling that the priority of the discovery of the element 113 will go to the group of RIKEN scientists. So it's quite a really exciting moment for me, and because that's a long year waiting for that kind of decision. So, and this is actually the first incident in Asia. The chemical element have been discovered, and I will explain a little bit about this things in this opportunity. So, still, this is a periodic table. Maybe you're familiar with this, and but the periodic table still now is evolving, and year by year. So the end of the last year, that's an element with atomic number 118 is recognized as a new element. And one thing for chemistry is it's a great moment that the seventh period of the chemical element have been fulfilled, and so that now the shape of the periodic table is very beautiful now. So keep in shape. So that, but okay, it's in future, but scientists want to destroy these beautiful things and to try to find out the new element in some new eighth period. Okay, it's a future story. And now we have know that the 118th elements, but the most of elements happen in nature, exist in nature, and they chemists try to find out from the nature things. Then the element with atomic number greater than 93 is artificially produced one, and element uranium, atomic number 92, is as a material which human can get at a certain amount in naturally occurring element. And after the neptunium 93 elements, we, the scientists, need to produce to find out this elementary table. So the element with atomic number 104 and above can be only made in extremely limited quantities. So and it is hard to prove their existence from the analysis of the chemical properties. It means that the chemical property should be studied in a little bit lot amount of the material is needed to investigate their chemical properties. So very little things is known about chemical property with atomic number greater than 104. Okay, it's quite more than 100 years before. Professor Masataka Ogawa find out a new element. In reality, he found out the element number 75 uranium, but he attributed its element atomic number 43. But unfortunately, atomic number 43 element is not exist in Earth because that's all the isotopes of the technetium. Now we call technetium is not exist. So that it's the Japanese first trial to find out a new element, but it's I mean that in a sense failed. And second chance will be the Nishina sensei of our ancestor. They also try to find out the 93 element, but also they could not find out a new element. So this is actually the third time for some Japanese scientists to produce a new element. And okay, so and their assignment of priority for discovery of a new element have been done with a so-called a joint working party. That's the member is listed here, and they examine very hardly and the priority of the discovery of the element. So I thank very much. That's a very intensive work and long-year work to assess that's the priority of the element. So that at the same time, that the element 115 and 117 and 118 also recognized as a new element, and the naming right goes to the collaborative team of Russian and American scientific collaboration. So that's I would like to congratulate them to also that they are very tough and sincere experimental works. But very it's my happy, but they also we could get the naming right for the element of 113. Okay, so okay, we try to produce at the 113th element, and we have succeeded to identify the event in 3 times. One is 2004, and second is 2005, and the third one is 2012. And this we detected only 1 atom in this year. So it means that we totally observed only 3 atoms. But these 3 atoms gave us the priority for discovery of the element. And we started the experiment the autumn of 2003, and we have continued the experiment from the 2003 until the August of 2012. So little more than 9 years experiment. And in 9 years, we only observed that the 3 events, but and also that's the collaborative team of Russian and American team produced the 113 element in a different way, and the reason why that's the naming right will come only our group and not go to the Russian and American team is just because of the fulfill the criteria of the element discovery. So that at the point which that's our experimental team fulfilled the criteria of the discovery of the element, that in the Russian and American collaborative team has not met the criteria. But it doesn't mean that the quality of the data is different. And quality of the data of the Russian American team is very fantastic, and that's why they can get the naming right of the 115, 17, and 18. So, and okay, and it's a point. And this is our experimental apparatus. And we have hole in a very, very big apparatus in RIKEN, exists in Wakoshi and near Tokyo. And the whole system is used for basic science and the nuclear physics. And also that is used to the applied science, biology. And our machine for creating the new element is that long circle colored by red dot. So, and this is our very, very first stage of the accelerator. It means that the speed of the incident particle, in our case, incident particle is zinc, and the speed of that zinc is 10% of light velocity. So it is 30,000 kilometers per second. It's a very slow one. So, and we use such a low energy beam to fuse the two nucleus together. So at higher energy, it doesn't fuse and it break up. So that we need to decide that very, very precisely that the speed of the incident particle, because that the atomic nucleus have a plus charge. So two plus charge repel together. So we need to put some energy to touch the surface of the nucleus. So that speed is very important, and we find that the 10% of light speed is the best to touch the two surface of the nucleus. Okay, so that's the in right hand side it's a gas field recoil ion separator is indicated, and I got the job in RIKEN in 1984, and after 3 years, from 1987 to 1988, I designed this apparatus and construct and to tune that one, and full scale experiment starts in 2001. So it's quite a long years. This is our tiny apparatus, and okay, very, very complicated say equation, and is 30 plus 83 becomes to the 113. This is only our equation. So, and we need to combine the two elements which give atomic number 113 and with two atoms. But this has a little bit severe reason to choose this combination, because that the bismuth is the most heaviest element in the stable atoms. That elements with atomic number bigger than 84, all that element is radioactive. So first, we want to avoid some trouble with radioactive target. We have chosen that's the heaviest stable material, and the counterpart is automatically defined when we can make apply this say formula. Okay, and then the first one came to the 2004, 23rd of July, and it takes 80 days after the first the day of start, and the second one comes 30 days after that. But the third one comes at almost 9 years after the second observation. So it's a little bit tough time for us to identify this third event. But okay, we have done. Okay, this is our little bit too much detail, but we need to accelerate the zinc ion up to the velocity of 10% of light, and to irradiate the bismuth target. And the form of the target is a very thin metal, and so beam intensity is so high that if we irradiate the target in stop static one, it evaporate immediately, so that we need to rotate very fast to avoid the heat damage. And then we need to select the particle which we want. There are a lot of beams, beam particles. The number of beam particles is 2 times the 2.5 times 1 million times 1 million. So we say 10 to the minus 10 to the 12th ion per second. So that's we need to select only the particle which of our interest. That Garis is such a device which I designed, and it has been we have been using this apparatus more than 25 years, and still the characteristics of this one is world highest level, and ions are implanted in some semiconductor, and then the decays are measured inside the silicon detectors. Okay, so the which isotope which we created the atomic mass number 278 and atomic number 113. But so our Russian friends produced that the element as well, and they produced at 113, 114, 115, 116, and 117, and 118. So 114s and 116s are already fixed, and in 2011, and then the rest 4 elements are now in the table of the discussion during these years. So then we got the naming right of the 113 case, and then that 115, 17, 18 goes to the Russian and American collaborative team. So you can see that the Professor Yuri Oganessian, and he's a scientific leader of this team, and in a sense he's my teacher, because that's I have learned much about this kind of job in Russia. I have stayed more than a year in total in Dubna in 1997, 1995. So, and I'm very happy to be given that the naming right with this very big boss. Okay, this is just a membership of our work, so that it takes 10 years. So in total, 48 collaborators in our work, but there are some already quit their work, and some newcomers comes. Okay, so this is a process, a naming process, and just okay, and first announcement came to me on the last day of the last year, and a real report appeared in the 21st of January, and the letter to invite us to the proposed element name and symbol just Saturday last week. So I have just received that official invitation to suppose. So we try to consider what kind of name will be given in the new element. So okay, so that's it's a quite exciting things, because that's our symbol will be in a periodic table in a sense forever. So that's some human beings scientific activity continues. If then it's a real fantastic for us, and very honor for scientists, and we enjoy this situation in 2 months, and the 1st of April is and the first deadline to that proposal. So we start to enjoy this situation. Okay, so okay, next step. So that I just told first that the next step will be that's a new element again. So that we need to break that's the very beautiful stage of that periodic table next. Okay, that almost all what I want to say. But there, some people ask frequently what is the usage of your new element, or what for was for the human daily life. But there, I should say, there are, now that there, I don't know any application of our new element, and because that's the lifetime of the element is 2 milliseconds. It's a very short time for in compared to our life. So we cannot create new chemical things or new material or new medicine. But for me, the important is that a new one. Well, we can find out the new element in the periodic table, so that the Japanese young people just start with their chemistry, see that this periodic table and look, okay, here is a element which the Japanese group have discovered. So then that I'm very happy they can feel something interesting in the chemistry, or such activities are very important for our scientists to educate or cultivate such a younger people to the scientific activity. So, and okay, so and the other sense is this is a basic science, mainly not for commercial base, but such kind of activity is very important for nation also. That's if we have a war condition, that kind of activity could not be happen, and we need to create the net basic science is a common knowledge for all the people in the world. So such kind of activity is very important for that for the nation. Okay, so this is some significance of discovery. Okay, that's all I want to present to you. Thank you very much for your kind attention.
Professor, thank you very much indeed. We've got a nice period now for some questions. I'm sure there are many, starting with the working press, and a question over there. If you could come up and ask the questions from the front. Thank you very much.
My name is Tim. I'm not sure if this mic is on, but anyway. Congratulations on this amazing achievement. And what was I going to say? Yeah, I think we're all interested to know what it might be named. I think the name, as you may have mentioned, I'm going to mangle the pronunciation, but Ununtrium, is that correct? Is the working name? But I think we're all expecting the formal name to be proposed. And what are the ideas that you're looking at to as a formal name for this element? Thanks very much.
Thank you very much for your question. And the naming right will come to the a group of the research group. So I cannot say personally before discussing with our person. So the letter which I received last week also indicates that your choice will not be publicized until that the IUPAC knows. So that's I'm sorry, but I cannot tell anything about the sample of the name, even that the sample. And sorry, but there are many guidelines for naming. For example, it should be end by IUM, and some relate to the mythology or some planetaries or some name of the place or some that's the very famous scientists already passed away. That's our selection. So that's within such selection we need to give a new name to the new element.
And how do you pronounce
Ununtrium? Ununtrium is some Latin number 113.
Can you say it slowly
thorium. Thorium, yeah. Welcome.
Any further questions? It's also sorry, but it has a potential chemical name already, right? That it could be described by its chemistry as well. Is that correct? Hang on, I wrote it down because I knew that I would forget it. Hang on a sec. That it could be ecothallium. Is that right?
Yes. But
Perhaps you can explain why it would be that.
So that's the element before the discovery. It's a meaning of the same group in the vertical row in the periodic table. That's the under the thallium means that's the eka-thallium. So, and for example, that's the for example, that's the germanium is element 32. That it is before discovered that element. That this element is tentatively called eka silicon, such a way. And so that's the eka-thallium is just meaning the same particle row, and under the thallium is the meaning of the eka-thallium. And chemical property should be quite similar, but because of their little bit too much scientific, but when the atomic number increases, so that because of their relativistic effect, the orbital electron, speed of the orbital electron come close to the light velocity. So nothing can exceed the light velocity. So as an element, the electron start to weight, so heavy. Then orbit shrinks a little bit. So then it changes a chemical property a little bit. That is a so-called relativistic effect. So now that there is no disagreement of the vertical row, but in the heaviest one, it should happen. So that's we don't know that there's any chemical property of this new element. So we cannot say this is just equal to the chemical property of the thallium. But they are now tentatively aligned this put in this place. Can I answer your question?
Yeah.
Sorry.
Sorry, there's sorry, can I take that question first? Thank you.
Khalil Hassan, I am Ambassador of Bahrain. I thoroughly enjoyed your presentation.
Thank you.
I'm very impressed by this research. Now, science is developing, technology is developing, and you are trying to develop new elements. My question is how far this is going to go and what you are trying to achieve. Let's say in 50 years' time, what sort of element you are dreaming to have to add to the elements we have just now? Thank you, sir.
Okay. Yeah, can I? Okay, so yeah, and the theorist speaks to us that the atomic nucleus exists at least until the 173. That's their expectation of the theorist. But their experimental point of view, we don't know how to create such a heavy element. So that now we are going very step by step. So at least, okay, in next 10 years, so we try to produce at 119 and 120, these two new elements in 10 years. This is my some personal view and which I'm trying to do next 10 years. So that's it needs definitely some improvement in technology, especially that the accelerator technology is a basic key point, because that's the the difficulty is the small probability of the fusion. So we know that the probability decreases with increase of the atomic number of production. And so when we get the event in reasonable time period, just we need to increase the instant beam per second. So now we are dealing with the 2.5 times the million and million one. So if we can get one order of magnitude bigger, then we can get 10. Now we takes about 10 years to get three events. So when we get the one order of higher, so only we need the 1 year to get three events. In that sense, that's the new accelerator technology to get the higher beam intensity is definitely we need. And then again, the next problem will be this is quite technical, but the target will not stand such high intensity beam. So we need to develop the target technology which stand to such high intensity beam. At least this 10 years we will do such a thing. But next, for example, 50 years, so we need to consider to another one of order of higher technique or idea of something different. So we need definitely some breakthrough to go further. So I don't know, but then in average, new element is discovered one new element per 3 years. This is some average until now. So that's the people can cope with such difficulties. And I don't know. Thank you very much.
最終的な目標は何ですか?
Okay. 最終的な目標っていうのはなんだっけ?
So final, what are you trying to achieve finally?
Okay, so I'm not a chemist, and that my specialty is the experimental nuclear physics. So that my dream is to find out the next island of stability next year. The neutron number for that island of stability is 184. Now we achieved 177. A few neutron more we need, but I don't know the way. But my final goal is to find out the nucleus with atomic numbers say higher, but the neutron number 148 is very, very important for us. That is say in a goal, but it takes 50 years, I guess. That's at least.
You had a question? Thank you.
My name is Shinomura. Thank you for a beautiful presentation, Professor Morita. I have two questions.
Yes.
One is, how many grams or picograms or how many particles did you make as a 113? That is my first question.
It's a B.
No, how many particles?
How many 130?
いくつ1グラムなのか?
3 atoms.
3 atoms.
3 atoms.
That's all.
That's all. Only 3 atoms.
My second question
Yes.
is the one you made hadn't exist before. How do you know it is it? How did you confirm
Yes.
it is 113?
Yes. Okay. And for first question only 3, but the second question, that this kind of heavy particle decays by say alpha decay, and alpha decay means the nucleus emit alpha particle. Alpha particle is consists of 2 neutrons and 2 protons. So atomic number becomes 2 less, and atomic weight decreases at the unit 4, and then this kind of things decays. The first 113 decays into the 111 element, and again that 111 element decays into the 109 element, and the 109 element decays into the 107. The 107 element also decay by alpha particle and become to the 105 element named dubnium. So, and 105 dubnium in the specific neutron number, I mean the atomic weight is 262 dubnium, is a very, very well-known isotopes already. So that that unknown particle, unknown 113 decays by alpha particle and reach to the known nucleus. So, and we can trace back that counting that alpha particle, emitted alpha particles, and half-life of that, I mean the decay time of that one, then we can conclusively, and we can unambiguously identify this one is the atomic number 113 and atomic weight of 278. This that the decays are connected into very well-known particles. Yeah.
One particle, right?
Yeah, three. You know. Yeah.
Yes.
Yeah.
And how to catch that small and very light particle?
Yes,
over
and
that long time?
yeah, and that the distance from the nuclear reaction take place and the detector is about 5 meters. So that the 100 particles of the 100 element passes through this 5 meters. And we applied the very strong magnetic field to remove that so-called background event and unwanted particles. So, and as much as possible, we can collect that efficiency. And then that small tiny particle are implanted inside the semiconductor made of silicon. And silicon is a very good detector of the radiation. So we can detect that event, the implantation, and just the same place, we observe that the alpha decay in series, so that the consecutive 6 or 4 alpha decay take place in the same position. We could know that position from the electric signal. So that we surely identify that all we can trace that all the decay process. That's why and how we can identify in such a way. Yeah.
So, Professor, can I just ask, sorry, just so I understand it, when the larger elements than, the heavier elements than unum trium were produced, did their alpha decay pass through 113 on their during their decay process? Yeah. For example, did 115 alpha decay to 113 before it decayed to 1111 and 119 and then down to But so that didn't count when 115 decayed to 113. That didn't count as discovering 113.
No, and it's should count it. Yes, so that's why the Russian and American group discovered 117, 115. It means automatically they find out the new element of 113. So that's the just I have stressed that the chronicle situation of the criteria match or not is just the assessment touched that only that point.
Right. So, is there a question there? Is there a question? Excellent, thank you.
Concha.
Please, yes, please.
I'm Ryoko Takeshi, working for the Asahi Shimbun News in Japan, and I have 2 questions. A little bit different from this question before, sorry. And first question is that could you give me a little bit more information about criteria you mentioned about? And the second question is that how did a Russian and American collaboration team did not match the criteria? What was the point? Could you tell me about that?
Yes, and the criteria, there are several criteria, and one is for example, it connects to the alpha decay connects to the known nucleus, is one criteria, and the other is some the experiment is reproduced by the different institute. Such a criteria exists also. And the most important criteria of which that the works in Russian and American group is the so-called cross reaction. The cross reaction means that the specific nucleus is produced by a different nuclear reaction. So, and the Joint Working Party decided to their recognition of 115 and 117 is they produce first the 115th, and then they produce at the 117, and just that one decays into the same nucleus of the 115. It the cross reaction. This criteria is worked in the 114, 16, 118, 113, and 117. Or
115.
115 and 117. And in 113, we have our chain connected to the known elements. And also we have make a cross reaction with a bombardment of curium plus natrium, sodium to produce that the great daughter of that 113 element. It means it's a 107 element. And then in the RIKEN case, that's the one criteria to connect to the known nucleus, and there is a cross reaction, and it fulfills the this criteria. At that moment, and that cross reaction of the 117 not take place. So that's why that's the that moment that is 115 and 117 is recognized as match the criteria is that chronically after our present publication of the other discovery of new element.
Excuse me. I want to make sure that the criteria which matched the more over 114 smaller than 113 a little bit different. I mean that you said criteria has 2 points, and one is that to decay to known elements, and the second one is that cross reaction to make sure whether it's or not. And so the elements over 114, Russian and American team also fulfilled both criteria?
No. And it's cross reaction is worked on element with atomic number larger than 114, and but the criteria is criteria, but in a scientific nuclear physics scientific consideration, that there are a lot of evidence to convince that that element is 114, 15, 16, but the criteria is not included such a things. So and the Russian team make for example, we call excitation function. It means that the energy dependence of the yield of that one, and that tells that the emitting neutron number, and the knowledge of the nuclear reaction mechanism. That it's quite sure that that one is a new element. But that kind of things are not included in the criteria this time. So that's all.
Okay, so Russian and American team fulfilled one criteria, but they had more and more supplemental information, so that's why they got the name right.
So,
Okay, thank you so much.
Any other questions? Is there sorry, can I just take this question from some?
My name is Kurt Sieber. I'm an associate member. Thank you very much for your wonderful presentation,
welcome.
but also for the very extensive documentation which you have distributed on this occasion, which gives us a very strong insight into the activities of RIKEN and Nishina. Thank you so much. My question is, and I'm going into one of these pamphlets which I received, and it says the powerful heavy ion beams will not only be used for nuclear physics research, but also for various application purposes. Could you give us a little bit, well, since we are kind of living on the earth here, we are asking for what are practical applications? How do you see the application field for this kind of research in the future? Thank you.
Thank you. And okay, I will tell first the existing application in our laboratory. The one is the to create the new plant with irradiation of that heavy ion beam, so that you can produce that the very strange colored flower or such things. That one is already in market, and we get 1 yen when that flower is sold. So such kind of things is one thing, and the other is we are creating that's the radioactive radioactive one. So for the I mean that's the for example in the laboratory or in the both in the biology or medicine, and we create and separate, and then we are selling that one. And the other one is for example to check the for example that we implant some radioactive material in the wheel of a car, and then that they can know that how much it's lost by detecting the radioactivity. So that's a check for the mamoってなんだよ。mamo is 3L.
I see. How much it's been not evaporated.
No,
but
Yeah.
worn down.
worn down there?
So you can tell when a tire needs to be replaced.
Yes, sure.
Right.
Yes, such kind of application. And the other is for example, you know that HIMAC and in Chiba, there are big accelerator to treating the cancer patient, and the basic study of that one is have made in RIKEN. So very basic one. So okay, okay. So I can tell more about that. Rather a lot of applications. Okay. One very important one is they can produce already that the rice. It's stand with seawater, and they grow not full seawater, but the half.
Salt-resistant rice.
Yeah, and and they grow quite normally, and taste not salty, and if that's they can produce that's the real one grown in the seawater level, then we can grow that the rice in ocean. So that's very helpful for that problem of the food. So such application is very many.
I think also if you look on page 20 of the pamphlet, the short pamphlet that we have, there's a picture of a kind of Japanese sake, which was which is made with yeast that was bred using the heavy ion. The smaller one. If you done that. Yeah, that one.
If you don't have it, there may be some copies outside. If
Yeah.
you have it here.
Okay, I forget to tell that my most favorite one. Yeah, sorry.
Exactly. Do you still have a question, sir? Thank you.
Your research is very interesting. You know, you are looking at depth. You are trying to create something. My question is personal. What made you, to go in this direction? In your life, in your research, what made you to think, I want to create a new element? What stimulated this in you? Thank you.
Okay, so it's just personal, my experience, and I entered the university, and the high school days, and the lecture of the physics is triggered me to I want to be a physicist. But in university, I'm not very good student, but I succeed to go to the graduate student and be a graduate student. But I cannot make my doctor thesis in the year, so I dropped out. And RIKEN, and picked me before getting a PhD. So that's I just started the RIKEN of this kind of job under the supervision of our senior researcher. So that's I have something I want to do at that time. I had something, but I said to him, and he told me that it's not interesting. So only creating new element is very interesting, he said. So I didn't understand what does it mean, but anyway, I involved because I have no doctor thesis or so. Okay, then I designed such a big device, starting from the beginning everything, and then with this apparatus, in the test experiment of superheavy element, we can create the new isotope of specific atomic number 87, francium. The name of the isotope francium 200. That is my first creation of new things. And then I write first my scientific article with that one, and it makes me some very, very strong impression. I feel it's very interesting to find out new things, and considering how to do such a way, and then we can make some additional technique to be added to find out new things. So, and by adding a new idea to find out new things, and after we get a new event, it feels very happy about that. So that's I can't not escape these things, and I very much involved deeper because of that experience. And that to start the heavy element job, I followed. Okay, we are totally newcomer to the new element research, so we should be in a sense we should be trusted. Yes, we should be trusted by other researchers, because we have no experience and no career. So I need to show our ability to the society. Then I decided to start with the little bit easier one. We have started with just follow the German group. We create the 108 first, and then 110, and 111, and 112. 112 is the most difficult one at that time. We have started the experiment. So then we could get just the same event as GSI people have done, Germany group have done. Then we have a lot of confidence to make a new one. So that's going to step by step, and the group of our group, everybody is very, very excited about this situation. Okay, let's go, and then it's very, very deep involved. Yes.
Thank you very much. But Professor, there was one thing that occurred earlier. You were talking about when the name is chosen for 113, that Of course, you will be very proud to see that on the periodic table, but also that it would have, it would be something that would inspire young Japanese to study physics and chemistry, I suppose. Do you think there's a risk that that science study in Japan is in decline, that there won't be as many Morita senseis in the future as there have been up till now?
Yeah, actually, that's the. I feel that the that just that real tendency that people or younger people don't like physics, and that population increases. I feel so that it's very danger for our nation, and the people who can make a scientific consideration, a scientific scientific manner is very, very important, and to do anything. So, if that's this new element discovered in Japan inspires that young people to get some scientific work, I'm very happy about that.
Sorry, just another question over there. Say,
yeah,
please, yes.
My question is about the slide there.
Yeah.
What is the difference of the days reaching to the observation? The first one was 80 days, and the second one is 30 days.
Yeah.
And then you took quite a longer days to reach the third manufacturing of making.
Yes.
What is the difference?
Yeah, this is just the statistics. Just okay. Which we know now is we can get 3 events in 600 days. That is all which I know. So if we take the average, that's one event will come in 200 days. That is the average. But the statistics is not just we thrown a dice. The probability of 1 is 1/6, but you don't realize the exact one. So we don't know anything about that which day it comes. But in average, it comes. So yes. And in a sense, fluctuation. Yes. Statistical fluctuation.
Sorry, what are the variable factors in that? I mean, what's the biggest variable in determining how long how many days?
It's the probability of the fusion. I mean,
Right.
Yeah.
Right. Sorry, it's right.
In other thing is the velocity of the incident particles.
Right.
So just important is the velocity just touch the surface of the nucleus.
Right.
And almost all the case it's reseparate, but in very small fractions that it start to fuse.
So these are the same environment, same environment,
exactly same,
three times.
Yes.
Right.
Yes.
Does that answer the question?
Just a random
probability. Sure. Yes.
Right.
And in this case, I'd like to indicate one more thing, that the first one and second one end by the fission of 1 or 5 element, but the third one is it decays by alpha particle, and then this dubnium 262 is known to decay by alpha in 60% probability, 66% probability, and it decay by fission in 33%. But it is a little bit strange, but it's a statistics.
Have you got one? Sir, have you got one?
I think you draw my attention to a very important point. Many people call themselves dropout, but they end to be geniuses. And you have many examples you already know. What is the defect that the geniuses have to be drop out? Is there a problem in the education? Thank you.
Excellent question, Professor.
Yeah. It's just lack of my talent of understanding the physics. And just, yeah, I feel very difficult to understand the nuclear physics. But why, and in a sense, I can recover and I could be some kind of scientist is okay, theoretical physics is very difficult. And in my case, that's experimental physics. If you know that's the method of the experiment, and you can find out new things. This is, in reality, scientific activity. Okay, it's not the real physics, but it's a scientific activity for me. And I can contribute in such a way. I found out myself, and just makes me a little bit stronger than before. And when I just drop out my scholar age. That's just I think that's in my short brain,
Thank you very much indeed. I think sadly, I think we probably have to conclude now. But thank you so much, Professor, for joining us today. And we hope very much that on the no doubt very long list of people that you will inform when you have chosen a name for 113, that the Foreign Correspondence Club of Japan will be first on your list of places that you will inform after, of course, the international scientific community. But thank you again for joining us today. And Foreign Correspondium is an excellent suggestion. Thank you again. And look, by way of thanks, this is a club membership for a year to the Foreign Correspondence, and I can't stress this enough. Please come and visit us. You're always welcome, as all our guests are, but particularly so after that presentation, and in an area that I wish we did more journalism on, because it's completely fascinating. So thank you, and thank you all for attending today. Thank you.
Thank you.